Okay, so the mileage of a certain car can be approximated by this equation. The question is, at what speed should you drive the car to obtain the best gas mileage? So after having seen that little video clip, you have an idea of what we're dealing with. Now, of course, this is not very realistic because odds are you don't have this equation in your glove box somewhere for your particular car. So if we wanted to figure out the speed of the car, the best speed, the optimum speed to drive the car, we could solve the problem graphically. So we could put it all into a graphing calculator and we could graph it, and we would get a curve that looks like this. And then based off of that, you can figure out where the optimum gas mileage is. Where is the best gas mileage? And you would notice that at the top of the curve, that's where the best gas mileage actually is, right at the very top. It has a horizontal tangent line. And horizontal tangent lines, of course, as we've been talking about in calculus this whole time, have a slope of 0. So you can use that little piece of information to help you know that the maximums, the best gas mileage, will occur when you have a horizontal tangent line, which is where the slope is 0, which is where the derivative is 0. This leads us then to something called the extreme value theorem. The extreme value theorem merely says that if a function is continuous over a closed interval, then f must have both a maximum and a minimum value somewhere in that interval. So in other words, remember, continuous means it has no breaks, no jumps, no gaps, no asymptotes. It's a smooth curve. And the interval is closed, meaning it has a stopping and a starting spot. Therefore, f must have a max and a min somewhere within that interval. These extreme values can be sometimes found in the interior or at the endpoints of a function. So for example, you have y equals x squared, and the domain is all real numbers. That would mean that there is an absolute minimum down there at the bottom at 0, but there are no absolute maximums because the function just keeps going on and on forever. Or you could have a closed interval, so it could be the same function, y equals x squared, but this time we're only interested in between 0 and 2 inclusive. That would mean it has an absolute maximum down there at the bottom at 0, and it has an absolute minimum down there at 0, and an absolute maximum up there at 2, 4. Sometimes you have one side is open and one side is closed. So in this case, it's open at 0 and it's closed at 2, which would mean there is no minimum because it never actually gets to 0. It just gets really, really, really close to it. But it does have an absolute maximum because it will actually get to 2, and that's where it stops. And other times you have an open interval on both sides, which would mean it has no minimum and it also has no maximum. Another name or another term that we use is we call local extrema. A local maximum is a maximum value within some open interval. A local minimum is a minimum value within some open interval. So let me give you an example of this. So we have a curve that looks something like this, and it would have an absolute minimum way down there at the bottom, you can see down there. And it would also, that absolute minimum would also be a local minimum. It has a local maximum at the top of the hill. Notice the difference that this is a local max, but not an absolute, because there is a point higher than that. It has a local minimum at the bottom of the hill. It has an absolute maximum up at the top where the spike is. That absolute maximum is also a local maximum. And then finally it has a local minimum at the end point. So you get the difference, the idea what the difference is between local mins and local maxes, and absolute mins and absolute maxes. We also, the book will sometimes refer to these local extremes as relative extremes. So you have to get used to the terminology. There's lots of different terminology in this section. Notice that the local extremes that are in the interior of the function, they occur when the function, the derivative of the function, is 0. At the top of the hill, that local max and that local min, they have horizontal tangent lines. Horizontal tangent lines, the derivative is 0. Or it can occur where the derivative is undefined, which is where the spike is. Remember when we talked about differentiability, functions are not differentiable when you have spikes or cusps like that. So those 2 points have slopes of 0, and the other point doesn't have a slope. Since we're talking about slopes, the slope of the tangent line, f prime of a, remember, is the derivative at a. the derivative is the slope of the tangent line. We've been talking about that all semester long, so hopefully you have that ingrained in your head right now. Derivative is the slope of the tangent line. This tangent slope interpretation has got lots of useful geometric implications that we're going to get into in this section. And the values of the derivatives, they enable us to detect when a function is either increasing or decreasing. And we're going to be talking about what do the values of a derivative tell us, how can we figure out when a function is increasing, how can we figure out when a function is decreasing. Now, if a first derivative is greater than 0 on some interval from a to b, then we say f is increasing on that interval. And for example, we have this situation. So we have a function that's increasing. The derivative is greater than 0. And you could see that the curve in that case is going up. If the derivative is less than 0 on an interval, so for example here, the derivative, all of those slopes are negative, they're all pointing downward, that would mean the function is decreasing on that interval. So if the derivative is positive, the function is increasing. If the derivative is negative, the function is decreasing. That then leads us into something called a critical number. A critical number c in the interior of the domain of a function, we call that a critical number under two conditions. First, either the derivative at c is 0 or the derivative at c does not exist. Okay, those are the two conditions for a critical number. You should write those two conditions down. So the first one, we have a curve and you have the derivative is 0, which means it has a horizontal tangent line. That's called a critical number. Or if it doesn't exist, like in that spike there, that would be an example of another critical number. Right, they are called critical numbers. C is a critical number, and when you do f, c, and f comma c, those are critical points. The only input where x equals c at which the derivative of a function changes sign, so going from either a positive to a negative or vice versa, are at the critical numbers. So, for example, remember critical numbers are 0 or undefined. Now, a local maximum, this is where we start tying these critical numbers together with maximums and minimums. Local maximums occur at a point, x equals c, if f of c is the largest value of f in some interval centered at that value. In other words, if it's a maximum, if it is the highest value of c, if it's the highest value of f of c within some interval. Global maximums occur at the point if it's the largest value of the function for every single x in the domain. Alright, so a local max is if it's the highest value of the function within some interval from a to b. Global maximums if it's the largest value anywhere in the domain. Local minimums, you can imagine, are very similar to local maximums. If a function occurs, our local minimum will occur at a point x equals c if it is the smallest value of f at some interval between a and b. And you see a picture there. A global minimum, absolute minimum, will occur at a point where it is the smallest value of f for every x in the domain. So notice the difference between local minimums and absolute minimums versus local maximums and absolute maximums. Don't get too hung up on the terminology right now. The main thing is, do you get an intuitive feel of what is a global minimum and what is an absolute, what is a local minimum? So let's put this all together and give you an example problem. I might ask you, I will ask you at some point, to find the critical numbers for a function. So you have this function, f of x equals x to the fourth minus 2x squared, and we want to find the critical numbers. Algebraically, what we're going to do, we remember that critical numbers occur if the derivative doesn't exist or if it's 0. So we take the derivative and we set it equal to 0. And then we solve it. So I factor out of 4x, I factor the x squared minus 1, and I wind up getting 3 different critical numbers. -1, 0, and 1. So pretty simple. Take the derivative, set it equal to 0, and solve. Those are going to be your critical numbers. Graphically, if we were to put this on a graphing calculator and we were to graph it and look at a number line graph, this is a convenient way to help us sketch out a graph. We know our critical numbers occurred at -1, 0, and 1. So if we were to test the first derivative for positive and negative, is it positive or is it negative? Very similar to what we did when we did number lines before, we could test the values of the derivative to see whether the function is increasing or decreasing. Remember, when the first derivative is less than 0, the function is decreasing. When it's greater than 0, it's increasing. So if I plug in different points, if I plug in -2, I get a negative answer. If I plug in -0.5, I get a positive region. If I plug in 0.5, I get a negative region. And if I plug in 2, I get a positive region. So remember, I'm plugging all of these values into the derivative to get an answer. Based off of that graph now, that number line graph, I know that we can identify the local mins and maxes based on what's happening here. So in that region, in the first region, it's negative, which means the function's decreasing. In the second region, it's positive, which means the function's increasing. Then it's decreasing again, and then it's increasing again. And so based off of these arrows, I can tell that -1 is a minimum, it's a local minimum, 0 is a maximum, and +1 is a local minimum. So to summarize, how do we find maximums and minimums analytically? First, find the derivative of the function. Set it equal to 0 or where it's undefined. These are called your critical points. Next, find the value of the function at the critical points. So plug your critical points back into the original function to find the value. Next, find values or slopes for points between the critical points. Make a number line chart, in other words, and use the number line chart like we did in the previous example to determine whether something is a maximum or a minimum. And then finally, make sure you check the end points. If you're dealing with closed intervals, sometimes the end points might be maximum and minimum, so you want to check those as well. For homework, so write them down, find the critical numbers of each function, and when you come into class tomorrow, we're going to talk about them.
That's all, folks.